Hello, Royals. Let's look at lesson 5.6. I want to do the examples with you and show you how to sort of illustrate and use sketches to help you out here. So we're going to be modeling periodic behavior with curves and then answering questions off of those curves. There's lots of different situations that you'll get used to seeing. A pretty popular one is a Ferris wheel, represents someone going up and down. Both their height and their horizontal position could be modeled by a sinusoidal curve. So Jack's watching his friend Jill as she rides a Ferris wheel, tracks her height measured from the ground. Jack knows that Jill reaches a maximum height of 11 meters at 10 seconds and then reaches a minimum height of 1 meter at 55 seconds. When you draw your sketches, I'm going to suggest that you both sketch the physical situation, if possible or if applicable, and the curve itself. Okay, so here's the physical situation. Here's a Ferris wheel. Look it up if you've never seen one. It's got an axle that is above the ground. That's going to be represented by the axis of the curve. The amplitude is going to represent the radius. The period is going to represent how long it takes to go around. Okay. Think about your axes when you draw this sketch here, because I would argue that Jill's height is dependent upon the time. So this 11, sometimes students just put in the point 11 comma 10, and that would be on the inverse of this relationship, which isn't a function. We don't even look at inverse trig curves in calculus. It's not, even post-secondary, they're not that useful. Now, what we've got here is evidence of a maximum of 11 meters, 10 seconds into the experiment, followed by evidence of a minimum of 1 meter, 55 seconds into the experiment. Okay, so you can go ahead and frame your curve there. Go ahead and draw a portion of the curve. And with this sketch, I feel like we're ready to go. This should feel an awful lot like the question that said a trig curve has a maximum of 11 after 10 degrees and a minimum of 1 after 55 degrees. We'll talk about the units, if possible, here as well. Okay? So use your sketches. Next, try identifying the sinusoidal properties. Like, for example, I like going for the amplitude first and then the axis of the curve. I find that it uses less memorization. For example, there is a total range here of 11 minus 1 meters. Jill is going through 10 meters of vertical distance. The amplitude is going to be half of that. I feel like I understand that instead of memorizing max minus min divided by 2 or max plus min dividing by 2. The students that memorize the formulas usually get amplitude and axis of the curve mixed up. Good. If my amplitude is 5, that would be 5 meters, by the way, but you don't need to worry about your units in your function. Then my axis of the curve is going to happen 5 meters above my minimum or 5 meters below my maximum. I can check it in both ways. Q is going to be 1 plus 5 or 6. And these are simple calculations, but it's a good idea to show your reader where you're getting your numbers from. Y equals 6. What other property am I missing? Oh, my period. Well, the time, the change in time from a maximum to a minimum, I can see on my curve is half a period. So let me record that 1/2 of my period is going to be the difference between 55 seconds and 10 seconds. So if half of my period is 45 seconds, that means that a full period is 90 seconds. 90 seconds to go around on a Ferris wheel. It's, I don't know, I guess it's a slow or larger Ferris wheel. The London Eye, or whatever it's called these days, it takes like half an hour to go around because it's so large and so slow. It's so slow that they don't stop it or slow it down for you to get on. It just goes by and you walk on and get off. It's kind of cool. All right. With my amplitude, I know my absolute value of A. With my axis of the curve, I know my Q value. With my period, I'm ready to find my K value. I probably don't want to think of this in terms of horizontal stretches. What would I stretch 360 degrees by to get it to 90 seconds? There's a unit conversion in there as well. When I say it out loud, it actually doesn't sound that complicated. You might hear it, but I'm going to suggest that you just rearrange a formula that you can build on your own. Your new period is a horizontal stretch of your old period. I don't want the horizontal stretch, though. This question didn't ask me to list my transformations. I know that my horizontal stretch is the reciprocal of the absolute value of k. All right. In this question, I know my new period. I know my original period. I'm looking for k so that I can write it into the function. And these are the parameters that I'm looking for. So I'm going to multiply both sides of this equation by the absolute value of k and divide both sides by the new period. Now, if memorization works for you, I suppose you could try memorizing this new equation. But students that try memorizing without a deep understanding often just do the reciprocal accidentally and they get the wrong answer. Like they deserve to. You should be able to develop this and understand how this works. So for us, the absolute value of k is going to be my original period for a sinusoidal curve is 360 degrees. I want my new period to be 90 seconds. This means that this k value is going to be 4. Maybe you saw that you want to stretch by 1/4 to get a period of 360 to change to 90. There's a stretch by 1/4. And then the lesson discusses the units a little bit. You can think of the units in a couple of different ways. Because this is circular motion, this is actually the angular velocity of any cog or any point anywhere on this circle except for at the origin. It's rotating through 4 degrees every second. But the other safer way to think about it is as a unit converter. And we'll see that when we do part B. So you don't have to include them in here. In advanced functions, there are a couple of questions where you need to know what these units are, and units are very important in calculus as well. So if you're planning on continuing those courses, make sure you pay attention to the unit portion of this lesson. Okay, have I already declared my variables? I have not. Let's get that out of the way. Let's let h of t represent Jill's height. Let's give a reference above ground. Is this in kilometers? Nope, in meters. And let's say it's t seconds. It's not t seconds since she got on the ride. It's not t seconds since she was at a maximum or an axis or a minimum. We actually don't know if anything special was happening at t equals 0. Turns out Jack started his stopwatch at maybe not a great time. All we know is he looked at his stopwatch, or maybe the wheel wasn't at full speed. So he started his stopwatch, realized that the wheel wasn't at full speed, and waited 10 seconds until it looked like the wheel was at full speed. Anyways, let's just say t seconds since observation began. Okay, nice, safe, non-committal declaration. So here we go. We want h of t to be a times sine or cosine of k bracket t minus p plus q. Not a bad idea to start with all of those parameters. This will make sure that you get it in factored form, because that's still important. And what do we know? We know the absolute value of a, the amplitude, the radius of the Ferris wheel, has to be 5. I haven't decided if I want to reflect it or not. Haven't decided if I want to use sine or cosine model yet. Pretty sure I don't want to horizontally reflect if I have the choice. K has to be 4 degrees per second. Haven't decided if I need a shift or if I want to shift horizontally. The axis of the curve, the height of the axle, has to be 6 meters. So this question can be challenging for a teacher to mark because there are an infinite number of correct answers. There's 2 very popular correct answers that most students will give here, using a non-reflected cosine curve, probably the most popular one, and then using a reflected cosine curve, second most popular correct answer. There's always more incorrect answers than there are correct answers as well. Okay. So from here, you have a choice to make. You weren't asked to define the equation. You're asked to find an equation. Okay. Since we have information about the maximum, and it's the first piece of information given, I'm going to choose to use a non-reflected cosine model. And then I can use the location of any maximum, the input of any maximum, as my phase shift. Okay. If you wanted to use a vertically reflected cosine model, you would need to shift right 55 degrees. There might be another shift you could use left, but I mean, it would require a little bit more work to do. That's not a great reason not to do it, but I mean, why not choose the most efficient approach? Fine. All right, for part B, I want to show you what this looks like with all of our units in here. Let me rewrite h of t. H of t is, so 5 was the amplitude. That was the radius of the Ferris wheel. That means it's measured in meters. That was the difference between 11 meters and 1 meters, which was 10 meters, divided by 2, which is 5 meters. Cosine doesn't have units. This 4 right here was in degrees per second, and we could figure that out just by saying our original period was degrees, our new period is seconds, so K has to be in degrees per second. T is in seconds. This 10 is also in seconds, isn't it? Sorry, I'm switching my S's around. And this plus 6, the axis of the curve, that was an average of the maximum and the minimum height. So at 2 is a height. It's the height of the axle of the Ferris wheel. That 2 is in meters. So that's what the function looks like with all of your units attached to any numbers. It's kind of a mess, isn't it? But it's interesting to see how the units eliminate or convert here. So when I substitute in 78 seconds, the input into this function should be a time in seconds. How is that going to switch to a height in meters? I'm going to take 5 meters multiplied by the cosine of 4 degrees per second. 78 seconds minus 10 seconds plus 6. And normally I would suggest to let your calculator do this work. In fact, I guess I'll show my work with the units here. So what is 78 seconds minus 10 seconds? That's going to be in seconds, 68 seconds. 5 meters cosine of 4 degrees per second, 68 seconds. So this is kind of problematic because I can't take the cosine of a time. I can only take the cosine of an angle, which is either measured in degrees or in advanced functions, unitless radians. That's the role of the k value here. When I take 4 degrees per second and multiply it by 68 seconds, I get degrees seconds per second. The seconds and the seconds eliminate, they divide, and I'm left with 4 times 68 degrees. 4 times 68 degrees is 272 degrees. So 5 meters multiplied by the cosine of 272 degrees plus 6 meters. Forgot my meters over there. Okay. Well, what's the cosine of 272 degrees? When my calculator gives me a number that's just a little bit bigger than 1, the cosine of an angle is a unitless ratio. This is where, all the way back in Unit 4, I think it's so important for us to understand not just what the angle and what side lengths are, but also that what the cosine ratio is. It is unitless. So I multiply 5 by about 0.0349, I guess. When I take a unitless measure and I multiply it by something measured in meters, I'm going to discover a quantity measured in meters. 0.174-ish meters plus 6 meters. And meters plus meters gives me an answer in meters. I wasn't given a level of precision, so I don't know. Okay, and that's how you change from an input in seconds to an output in meters. You can ignore most of that and let your calculator do the work and trust that your output will be in meters, but it's quite important in advanced functions and calculus to get how these units work. I suppose we also should have been able to check this here. If we had drawn our sketch, we would have noticed that 78 seconds is just a little bit past an axis point. With what was our full period? With a full period of 90 seconds, a quarter period is going to be 22.5 seconds. If I go 55 seconds forward, then I'll be at this axis height, or Jill will be at that axis height at 77.5 seconds. So we're talking about 0.5 seconds later. In fact, I would have been impressed if a student had just said, well, it's going to be around 6 meters, isn't it? Maybe more impressed than being able to just substitute in here. Okay. Next question says, when during the first minute is Jill 10.5 meters above the ground? Let's go back to our sketch. We have a maximum height of 11 meters and an axis height of 6 meters. This is kind of like solving a trig equation. using a sketch. Standard position is not going to help you here. Looking on our sketch, I'm thinking that we should be at a height of 10 meters, just a little bit before 10 seconds, and that same should be symmetric here. Same distance afterwards, and then we'll see if we can figure out during the first minute. I don't think during the first minute that it happens again, because this is like 55 seconds later. So I'm pretty sure that this is time 1 and that's time 2. I might be wrong. I can always change those later. Okay, I'll be scrolling up to see that sketch in a sec once I find one of my solutions. So I'm going to set h of t to be 10.5. I'm not going to answer this question through trial and error. That's never really been a suggested approach. That means I want 10.5 to equal 5 times the cosine of 4 bracket t minus 10 plus 6. And you're going to solve this trig equation just like you solve a quadratic equation by isolation when you complete the square. There's no quadratic formula that's going to do it for you. Solving by factoring isn't really that great of an approach anymore. You need to understand how to undo operations in reverse BEDMAS order. Let me try undoing these operations a little bit faster as well. I suggested this earlier, I think, in a previous lesson, maybe not having to show every single step. Do we get that it's like a cake? You have to remove these outer layers before you get to the inner layer. So the last thing I'm going to undo is the 10. Before that, I'll undo the 4. Before that, I'll undo the cosine of. Before that, I'll undo the multiplication by 5. The first thing I undo is the plus 6. So I'm going to subtract 6, divide by 5, take the inverse cosine of, divide by 4, add 10. See how you feel about doing all of those. Maybe not in one step, but just leaving space around so that you don't have to write. What have we got? 1, 2, 3, 4, 5 operations to undo? I don't know. Like, teachers encourage you to show all of your steps, but I think very few teachers would encourage you, unless you're really struggling with this, to actually take the time to write down all 5 of those steps. The other, I think, comment here is that maybe sometimes students want to see that subtraction so that they can type in what is 10.5 minus 6. I'm not going to type in anything here until I get to the end. I don't need to touch my calculator until the end. So what am I going to be doing? I'm going to subtract 6 from both sides first. Then I'm going to divide both sides by 5. That'll leave me with that. Then I'm going to take the inverse cosine of both sides. That has to go to the left. Just like a square root, you can't write times cos inverse. That's nonsense. After I take the cosine of, I'll want to divide by 2. I'm going to change my mind. I'm going to multiply both sides by 1/4. So I don't want to divide this thing by 2. Let's multiply it by 1/4. And then the last thing that I'll do is add 10 to both sides. Okay. So I am doing things one step at a time. I'm just showing all of those steps on one line. The unit conversation is kind of interesting here as well. This 10.5 is in meters. I subtract 6 meters from that. Of course, I can subtract meters from meters. I divide that by meters. That gives me a unitless ratio. I can take the inverse cosine of a unitless ratio and then multiply by 1/4. That is going to be in seconds per degree. Or sorry, this would be an angle in degrees when I take the cosine inverse. In degree mode, I multiply that by seconds per degree. The degrees eliminate. I'm left with seconds. I add 10 seconds to that, and I get an output in seconds. It's another situation where you might want to kind of trust that it works. So touching your calculator once, if you want to go through the steps with your calculator, you can. 10.5 minus 6 equals, divided by 5 equals, inverse cosine of that equals, divided by 4 equals, plus 10 equals. But I'm not writing all of those numbers down. I'm not approximating 5 different times. The other option, and something else you might want to try doing just to make sure you haven't made any mistakes here, is you should be able to type this in one go. 1 divided by 6 multiplied by the inverse cosine of bracket 10.5 minus 6 bracket divided by 5 bracket plus 10. Hey, I wasn't 100% confident there, if you couldn't tell. Okay. Oh, right. So I was a little surprised here because I get the answer 16 seconds. And I was surprised because 16 seconds is actually larger than that 10 seconds. I'm not going to change my diagram here, but what I forgot to account for is the fact that this was an original cosine model. So if this was the y-axis, my calculator is thinking that is the first solution. Turns out this solution back here actually comes before the first solution. It's a solution that I would have dismissed normally because it would be in the negatives, but because of the phase shift here, it's in the positives. Not a problem. All I need to do is change this label down here. Turns out that that's time 2. Okay. I'm going to draw the zoomed in portion of my curve down here so that I don't have to keep on going up. This maximum happens after 10 seconds. I figured out that I'm at this height after 16.5 seconds. Okay. Let's use the symmetry of this curve and show our work. This isn't really an angle anymore, so I'm not going to call it that gamma that I've used before. I'm going to call it delta t, a change in time. That change in time that I'm looking for is the difference between 16.5 and 10. 6.5. Because of the phase shift, this curve isn't symmetric about its dependent axis anymore. You can't do 1 period minus this or 180 degrees minus this. Again, this is where standard position really falls on its face. This means that time 1 is going to be about 10 minus 6.5, or about 3.5 seconds. Okay. Use your sketches to find these other solutions. Your calculator will tell you one solution. I needed my calculator to get one solution here. Standard position worked okay, but it's like training wheels. And now it's time to take off the training wheels and use the curve. We should have been answering these questions with full sentences. She was 10.5 meters above the ground. 3.5 seconds and 6.5 seconds after observation. In advanced functions, this would just be an inequality question. You would figure out when was she greater than 10.5 meters above the ground. And you would just use your sketch to say, well, in between those times. You don't try to solve the inequality algebraically in advanced functions. Okay. On the back, we don't have as much to do. We have the top of a flagpole swaying back and forth in high winds. A little exaggerated, but that's all right. The top sways 10 centimeters to the right. Looks like we've defined that as positive, and 10 centimeters to the left of its vertical position, and it moves back and forth 120 times every minute. At t equals 0, the pole was momentarily at its resting position, then it started moving to the right. So this is telling you to use a non-reflected sine model. Determine the equation for a sinusoidal function that describes the distance the top of the pole is from the resting position in terms of time. So this flagpole is at rest, then it is going to move to the right. This is going to be, the challenge in this question is that I'm using a vertical axis to measure a horizontal distance. That's going to be 10 centimeters to the right. That's at rest or vertical. That'll be 10 centimeters to the left. This is the distance as a function of time, and this is the time. Declaring our variables should tidy this up a little bit. Let's let d of t represent the horizontal displacement of the top of the pole in centimeters. And you could say, for a reference, we could say from the vertical. I feel like we might need one other thing in here. It's kind of in the question itself, but let's just define a direction as well and say where right is positive. Just be as specific and precise as you can here. Okay. The reason why the rest of this should go quite a bit faster is because I'm pretty sure we need an axis of the curve of y equals 0, an amplitude of 10, so and no phase shift, so I'll use a non-reflected sine model. The last challenge is dealing with this period right here. The 120 times every minute isn't going to be the period. That's more my frequency. And I recognize now that I didn't declare my independent variable. Let t represent, it didn't tell me which units to use. I think we should convert it to time in seconds. Now we do have a reference here. I don't think saying since observation began is the most appropriate let statement. We just need to be wordy. Let t represent the time in seconds since the pole was vertical. And moving right. Like I said, just be as specific as possible. And sorry about the handwriting. There's stuff in my way here. And my handwriting is also terrible by default. Okay, so for our period, make sure that your period is measured in the same units as your independent variable. If you think that your period should be 120, that is times per minute. And if your independent variable is in minutes, this isn't measured in minutes either. Right? Let's scratch that out because that's wrong. Our period is actually 1/120th of a minute. And to convert, just try multiplying by 1. In 1 minute, there is 60 seconds. Minutes divided by minutes will eliminate, and you will get a period of 1/2 of a second. If you're thinking about your work, you will usually catch that 120 isn't the length of time that it takes for anything to happen here. It's not 120 seconds for this flagpole to go backwards and forwards. It's going quickly, maybe a little bit too fast. It's like some kind of pendulum or metronome. Okay, one more time with this k value. Our new period is a horizontal stretch of our old period. My horizontal stretch is the reciprocal of the absolute value of k. I don't need to know what my horizontal stretch is in this problem. I want to know what my absolute value of k is. Multiply both sides by the absolute value of k, divide both sides by your new period. You will get 360 degrees divided by 1/2 of a second, or 720 degrees per second. Since there's no circular motion in this question, this is not how fast this angle is changing. It is purely a conversion factor. Okay. And here we go. Probably the most popular function that we would use would be d of t is we need an amplitude of 10. I'm going to use a non-reflected sine model. Advantage there is that I don't even need a phase shift. 720 t and plus 0. And there you go. Okay. Draw sketches of the situation, draw sketches of the curve. Think real hard about developing these formulas instead of memorizing them. Declare your variables specifically and precisely, with full sentences and units and references if you need them. This material is returns again and is still important in advanced functions. So make sure you practice it, especially if you plan on going forward into advanced functions.